In this video, we're going to go over the product and quotient rules, which are two rules that you can use when trying to find the derivative of a function. What I'd like you to do right now is pause the video and try the warm-up questions. You're given several functions and I'm asking you to differentiate each function, which means take the derivative of each function. Okay, at this point I hope that you've tried each one. Let's go over them. So for question number 1, you're being asked to differentiate a function that is a constant. So if you remember from our constant rule, the derivative of a constant is always equal to 0. So that would be number 1. For number 2, we could use the power rule. For each term, the sum and difference of these terms can each have the power rule applied to them individually. So the derivative of x to the third would be 3x squared. The derivative of negative 4x would just be negative 4. So when I brought down that power of 1 and subtracted 1 from the power, I end up with x to the 0 power, which is just a factor of 1. Again, if we want to write that out, we can. And the derivative of 6, which is a constant, would just be 0. So the simplified derivative here would just be 3x squared minus 4. For number 3, before I go about taking the derivative, I would want to distribute this 1/4 because I want to be able to look at each term individually, not as a product of terms. So I would distribute 1/4 to the t to the 4th, and 1/4 times 8 would just be 2. So now I'm going to apply the derivative power rule, bring the 4 down. 4 times 1/4 would just be 1. Minus 1 from that power, you would get 3. So 1 times t to the third would be the derivative of the first term. And again, derivative of a constant is 0, so that would be the full derivative function of f of t. For number 4, we're trying to find the derivative of x to the negative 2/5. So using the power rule, I would bring down that power, negative 2/5. And then subtract 1. Again, remember when you're subtracting 1 and you're dealing with a fraction, nice idea to just make it an equivalent version of the number 1 using that common denominator. So negative 2/5 minus 5/5 would be negative 7/5. Again, we always want to make sure our final answer is left with positive integers. So I'm going to first use the negative exponent rule, which says I can bring x down into the denominator here, which is really taking the reciprocal of x over 1, making it 1 over x. Now my power is positive 7/5, but it's still not an integer, so I would now want to rewrite this using an equivalent radical expression, which would have the 5th root of x to the 7th. Now technically you could take this a little bit further because inside x to the 7th we do have a factor of x to the 5th, which would be a perfect 5th. So you could take this one step further and rewrite this as 5 times x times the 5th root of x squared. Okay, and let's take a look at just 2 more. For number 5, we have a function that's equivalent to x to the 1/2. Again, you always want to make sure if you're using the power rule that your function is in this format, some constant coefficient times x to a power. So again, you don't want x to be under a radical. If it is, please rewrite it using an equivalent fractional exponent so that you can then apply the power rule. So I'm going to bring down that power of 1/2 and then subtract 1 from 1/2, which would give me negative 1/2. Again, just to review, use 2 over 2 when you're subtracting 1 so that it's easier to find that difference. Now, because the power is negative, I'm going to bring x down in the denominator, with 2, so I can make the power positive, and then one step further, rewrite it as the equivalent radical expression, which would be the square root of x. So 1 over 2 times the square root of x is the derivative of the square root of x. Now, for question number 6, this is not written in polynomial form, so I need to, if I'm going to use the power rule, I would need to see this written out as a string of terms, polynomial terms, not as a set of 2 binomial factors. So I'm going to start by distributing. And now that I've distributed x and -2 to the 2x plus 3, I'm just going to combine like terms. So I have 2x squared. I had positive 3x and -4x. That's going to give me -1x minus 6. Now I'm going to use the power rule to each term. So I bring down the 2. 2 times 2 is 4. X to the first minus 1. Really, this would become x to the 0. And again, the constant would have a derivative of 0. So to simplify this, h prime of x would just be 4x minus 1. Final answer. So again, hopefully at this point we feel comfortable using the power rule to find the derivative of various types of functions. What we're going to be reviewing, learning today, and then we'll be spending the next couple of lessons practicing, are 2 additional rules, and I want us to keep number 6 in mind. Even though we had a way of finding the derivative of number 6 by multiplying the function out and writing it as a standard form polynomial function, there is another way to go about finding this derivative using one of the rules we're going to learn today. So the first new derivative rule that we're going to learn is something called the product rule. So what this rule says is if you have a function that is made up of the product of 2 functions, so something like number 6, you can think of x minus 2 as a function and 2x plus 3 as a function. So h of x is really made up of the product of these 2 functions. As long as both of those functions are differentiable, meaning you can take the derivative of them, then the derivative of that function, again, let's just kind of take this step by step. So this is my original function, f of x, made up as the product of u and v. Then the derivative would come out to be this. So let me just explain what we're looking at here. So the product rule says if you take the first function, u, and take the product of that function and the derivative of the second function, that's this part here, u times v prime, and then you add that to the product of the derivative of the first times the second function, that will give you the derivative of the overall function. Now it's written also in words here, just if that's an easier way to think, to look at it. So the product rule says that the derivative of a product of 2 functions is the first function times the derivative of the second function plus the derivative of the first function times the second function. So when we use the product rule, I will often first name each function. So let's revisit this was actually number 6 from the warm-up, but we're now going to find the derivative. Even though we know the answer, we're going to find and try to prove that we can get to the same derivative using this product rule. So first I'm going to say that x minus 2, this is my function u, and 2x plus 3, that's my function v. And off to the side, before I even start using this rule, I want to think about what is the derivative of u and what's the derivative of v. So if I just look at u as its own separate function, x minus 2, the derivative of that would just be 1. Right? You'd bring the 1 down in front of the x. 1 minus 1 would be x to the 0, and the derivative of -2 is just 0. So the overall derivative of u would just be 1. The derivative of v would be 2. Bring the 1 down again in front of the 2. 1 minus 1 would give me 2 times x to the 0. Again, x to the 0 is just 1, and the derivative of the 3 would be 0. So here are the derivatives of my 2 functions. And now we're going to apply the product rule. So if I want to find the derivative of h, I'm going to take the original first function, which is just x minus 2, and times that by the derivative of the second function, which is just 2. Right? So there's my u times v prime. Now I'm going to add to that the product of the derivative of the first function, which is 1, that's my u prime, times the original second function, 2x plus 3. That's my v. So now I'm going to simplify this. So if I distribute the 2 into the x minus 2, I would get 2x minus 4 plus 2x plus 3. Since we're just distributing a 1, let's combine like terms. We get 4x minus 1. And if we go back to our warm-up, we also got 4x minus 1. Now, for this one, it might have seemed like a lot of work, but you're going to see after we do a couple of these that sometimes this will actually save you time. In this question, if you really wanted to just multiply out the two factors, x minus 2 times 2x plus 3, and then apply the power rule, to avoid the product rule, you could. You really could do that if the functions are things that you can multiply together nicely. But this rule, the more you become comfortable with it, you will see that it can save you time. So let's look at number 2. I want to first think about this as two factors, two separate functions. So even though they're the same function, we're going to call one u, we're going to call one v. And we're going to say, okay, the derivative of u is 1, and since they're the same function, the derivative of v is also 1. So if we wanted to find the derivative of g of x, we would take the original first function, which is x plus 1, times the derivative of the second function, which is 1. So again, this is u times v prime, plus the derivative of the first function times the original second function. So u prime times v. So now I'm just going to simplify this. X plus 1 plus x plus 1 would give me 2x plus 2, and that would be the derivative of this function. Let's try one more product rule question. Now, for question number 3, again, you have the option. If you wanted to, avoid using this, let's say it was a test and the question was just, here's a function, find the derivative, and I don't tell you specifically what rule I want you to try, you could multiply this out and use the power rule. But now we have a trinomial times a binomial. We have some higher powers. It might just be simpler to look at this using the product rule. So let's call 2x squared minus 5 our function u. And let's call the 3x to the 5th plus 4x minus 1 function v. Now let's find each of their derivatives. So u prime, I'm going to take the 2, bring it down in front. That would be 4x to the first, and then minus 5 would just have a derivative of 0, so just 4x would be the derivative of u. The derivative of v, I would get 15, 3 times 5, x to the 4th from subtracting 1, and then bring the 1 down, plus 4, x to the 0, so we'll just leave that as plus 4. Minus 1 would have a derivative of 0. Now let's find the derivative of this overall function. So we're going to take the original first function, 2x squared minus 5, times the derivative of the second. So v prime was our 15x to the 4th plus 4. So again, u times v prime, plus the derivative of the first function, which we got 4x, times the original second function. So again, this is u prime times v. All right, so I don't have a ton of room that way, so I'm going to write below. So let's do some multiplying now. Now it's just really up to multiplying and combining like terms. So we get 30, 2 times 15, x to the 6th, since we have x squared times x to the 4th. Then 2x squared times 4 would be 8x squared. Minus 5 times 15x to the 4th would be minus 75 x to the 4th. Minus 5 times positive 4 would be minus 20. Now we're going to add to that the product of 4x and 3x to the 5th plus 4x minus 1. So let's distribute the 4x. We get 12x to the 6th plus 16x squared minus 4x. Okay, so we are done distributing. Let's combine like terms. So we have two terms here with an x to the 6th, a 30 and a 12, x to the 6th would add together to give us a 42, x to the 6th. Let's look down now. What's our next highest power? I think I see this term here with the x to the 4th, so minus 75, x to the 4th. We have a few terms here with x to the 2nd, so let's add them up. 16x to the 2nd plus 8x to the 2nd would be 24, x to the 2nd. And then one term with negative 4x and a constant of negative 20. So negative 4x minus 20. And now we should have the simplified derivative for this function that started out as r of x. So this is r prime of x using the product rule. Okay, So now what I'd like to do is talk about a rule that we can use when we're dividing functions, and we call this one the quotient rule. So the quotient rule, we take a look here. If you have a function made up of the quotient between two other functions, we're going to again call them u and v. So if you have u of x divided by v of x, like we have here, then the derivative using the the quotient rule would come out to be the following. So we're actually going to start this one with the denominator function. So when we refer to it as the first function or the second function, the first function is the numerator u, the second function would be the denominator v. So we're going to take the second function times the derivative of the first, so that's v times u prime. And now we're going to use subtraction here. So minus the derivative of that second function and the product with the first function, so v prime times u. And this whole difference is going to be divided by the squared denominator, so the second function squared. So again, that's described for you below in words, and we're also under the assumption here that the denominator function cannot equal 0, otherwise this would become undefined. So if we take a look at number 1, we're going to say u is x, that's our u function, so u prime would just be 1. So the derivative of the numerator is 1. The denominator function v is what we're calling the x squared plus 1, so v prime would be 2x plus 0, or just 2x. So if I want to find the derivative of f of x, the quotient rule states I would start with the original denominator function, or the original second function, times the derivative of the first. So here's my v times u prime, minus the derivative of the denominator, which was 2x, times the original numerator, which was just x. So this is now v prime times u. This whole thing is going to be divided by the denominator, or the second function, x squared plus 1, squared. So now we'll just do a little simplifying in our numerator. X squared plus 1 is just multiplying 1, so that's just going to be x squared plus 1, minus 2x times x, which would be just minus 2x. Again, all over x squared plus 1 squared. We could clean this up just a little bit more in the numerator. Combine those like terms of x squared and negative 2x squared to get negative x squared plus 1 over x squared plus 1 to the second. Now technically the numerator is the difference of two perfect squares. If I rewrote it and put the minus between them, it might be easier to see that. So technically if we wanted to, we could factor, but this factoring isn't going to lead us to a more simplified answer, because x squared plus 1 is not the difference of perfect squares, it's the sum. So technically any version of what I have down here would be considered the simplified derivative. The original final answer we got here, yes, it can be factored, but the factoring doesn't help us get our answer into a more simplified form, so really it's unnecessary to factor it. Okay, let's try another one. We're just going to do 2 more. So for number 2, we have a function, g of t. The numerator, we're going to say this is our u function being divided by our v function. So off to the side, let's find the derivative of each. U prime would be 2t, v prime would be 2. So using the quotient rule, we're going to start with the original denominator times the derivative of the numerator minus the derivative of the denominator times the original numerator, all divided by the denominator squared. So now let's simplify this a bit. 4t squared minus 14t minus 2t squared minus 4 all over 2t minus 7 squared. And we'll take this one step further to simplify the numerator. 2t squared minus 14t minus 4 over 2t minus 7 squared. Now, technically, similar to the last question, we could factor the numerator. We could factor out a 2, t squared minus 7t minus 2 over 2t minus 7 squared. But again, that doesn't allow us to simplify any further, so either version here would be an acceptable final answer for the derivative of g. And now for number 3, let's go about this quotient rule one last time. So here's function u, here's function v. U prime would be 10x. V prime, because the denominator is just a constant, would just be 0. That's going to make some of our simplifying a little bit easier. So we're going to take the original denominator function times the derivative of the numerator minus the derivative of the denominator, which is 0, which is why this is going to be a little bit nicer, times the original numerator. So since we're multiplying something here by 0, we're going to simplify that all over the denominator squared. So we end up with just a numerator here of 40x, 4 times 10x, because this becomes 0, over 16. And then I can simplify that. So let's reduce 40 over 16 is 5 over 2. You could leave the x in the numerator, put the x off to the side. Either way, that would be our simplified derivative for this function y. So please look back through this video, go back to any of the questions, or go back to the original rules to review. And what I would like you to do right now, at this point, just watching the video and taking notes up to question 3 for the quotient rule is what I hope you were able to get through. There are practice questions that I would encourage you to look at, and the notes will post by the end of today so you can check with the key later. This homework will not be due until Friday, so we're going to review this together tomorrow in class.